some more mobile than others, and some look like an impurity, which gives rise to that impurity disorder for atoms, which are then your Bose-Hubbard atoms. And that's an experiment that Dominic did, and I'll tell you about what he saw in that experiment tomorrow. Okay, so almost on time. So here's what I told you about today. Just to sum up, I told you about the most widely kind of employed disorder, speckle disorder, and I told you more about it than almost we ever talk about, which is almost nothing about the topic. So I encourage you to read books and papers if you're more interested and want to know about some of the perverse features of speckle. I told you about projected disorder, which really just Emmanuel Bloch's experiment is using, which is kind of like a version of speckle but controllable. I told you about incommensurate lattices, which have been used by many groups as a kind of pseudo disorder. Okay, and then I told you about impurity disorder, which has really been used by one group. And I'll tell you what they observed. And they compared localization in that kind of disorder to localization with impurity disorder in a really beautiful paper. Okay, and that's it. All right, so you can trickle out. I think Vadim has a question. Go ahead. Right.
The reason this is better for full values is because somehow the time scale to actually one complement value is much more than one.
Yeah, so I'm not sure that classical trapping is a huge, terrible, bad thing, but it's a problem in the sense that if you just want to do experiments and look at what you measure and try to figure out what's going on, you can get a regime where you see just what classical turning trap turns into for quantum particles, which is like locally bound states, right? And have difficulty distinguishing that from other things. And it may be that tunneling, really, those stuff gets coupled through the barriers, but that time scale may be quite slow and then, difficult to, you might see that and think you see localization, and indeed some people got tricked by things like that in 1D. Yeah, go ahead.
So when you have speckles, so when you have these nodal lines in the speckle,
yeah.
people actually try to carefully tune into that regime and look at properties when the particles are primarily seeing the potential from nodal lines.
Yeah, so I think your question is like, if people looked at, can you see physics of particles propagating through those nodal lines? And
I think that there's localization because they're not straight lines.
Well, yeah, so those lines are funny. I mean, those lines actually wander fully in 3D, and this is not appreciated by everyone. So there's that characteristic length scale, both in transverse and longitudinal directions, right? Which is the length scale associated with the intensity autocorrelation. So after one length scale, in any direction, that nodal line, its direction is randomized. So it'll propagate, and then if you go look statistically after a local, it's going some random direction flowing in 3D. So no one's seen a big impact of those on experiments that we can tell, but I really don't know what role those are necessarily playing.
But is it possible to line up these nodal lines?
No, you're not allowed to line up these nodal lines. They have to, by physics, wander in 3D fully over a speckle length scale.
If you line them up, it would be an optical lens.
Yeah, there's actually interesting experiments. I think it would be really cool. You could, I don't know if this is allowed by Maxwell's equations. I've never figured it out. But it'd be cool to make a bunch of dark lines which are kind of randomly, separated from each other, which go straight, and then see what happens with physics in that. I'm not sure it's allowed by Maxwell's equations.
Then it's going to be a clean problem. But
Yeah.
somehow to line them up enough that the system is marked with an isotropic.
Yeah, so there's a whole field of Fourier optics where people, and I've published a little bit in that field, where people look at the extent which you control light fields. And it's not always easy to figure out what Maxwell's equations let you do and don't let you do. Especially in 3D, it's very confusing. In 2D, I have a pretty good intuition what Fourier optics allows and doesn't allow. In 3D, it's confusing. And that's kind of what people like Miles Paget and other people work on, is controlling a light field in 3D and figuring out what you can do with it. And for me, it's not always intuitive what's allowed and not allowed. So I don't know the extent to which you can control these nodal lines. Yes, please.
These lines, then can you get to like a critical point where they like extend through the whole thing and like connect with each other? Or?
Well, they're not allowed to connect and disconnect with each other. That's not allowed by Maxwell's equations, all right? So these lines are separate from each other always, okay? And they just wander around.
So then, if they can't connect with each other, then after a certain density, then they must interact, and that, like, they affect where neighboring lines can go.
Yes, yes. But honestly, the experiments with ultracold atoms in these potentials, as far as we know, I don't know to the extent to which these lines have played a role. You know, people have done basically two things. People have controlled the amount of disorder by controlling the amount of light, right? And these lines and the features of the speckle are doing whatever they do. And as far as we can tell from all the theory that's been done, the main things that control localization are the amount of disorder present, which is controlled with the amount of light, and then really the power spectrum or the Fourier spectrum of the disorder controls how the particles scatter off of it, right? Because the atoms wander around in this disorder, and what it looks like is there's some limit in which they're plane waves, and then they kind of scatter and change the direction, and scatter and change the direction, like Vadim was saying. And that's controlled by the Fourier spectrum of the disorder, that process, right? And Vadim also wrote something down that looks just like that. And so as far as we know, the statistical properties of the speckle capture all the physics that's been seen. And that leaves out all these nodal lines, and I don't think people really know what they're doing or what role they're playing. But I think it's an interesting question. Especially because different groups have done different things. Like, people have turned on the disorder slowly, which you might imagine forces the atoms into some of these nodal lines. Other people have turned the disorder on very fast. Maybe that does something different, although no one's ever seen a difference. So there are great theory questions there that are hard questions, which is why they're still out there. Yeah?
Has a linking of these nodal rings ever been observed? Or
Yeah, I think one group has seen these nodal rings be linked. One of these optical physics groups. But it's a really rare, it's possible, but it's very rare.
Did anything interesting associated with that?
In optical physics, sure. I mean, for localization stuff, so those vortex rings, we know the the intensity barrier around that ring, right? That's a well-defined quantity. Like, there's a 0 and you go away from it, and then there's maximum intensity you'll encounter before you get out of there to another local minimum another saddle point. And we know that intensity barrier, and it's really, really small. In fact, it's too small to trap any atoms in those rings for any experiments that have ever been done. Okay. All right, so last lecture for me tomorrow morning. I think I'm the first one. See you then.
Just two things. So tomorrow we'll start at 9:30 again. Breakfast will be served starting from 8:30. And for dinner, you guys can go to Nassau Street. There are a bunch of restaurants. And if you like burger, I recommend Triumph. They make their own beer. So that will be a good try. And so that's it. Enjoy Princeton. Thank you.